my students. Welcome to the part 3 of lesson 4, Miscellanea of Trigonometric Results. And today I'm going to try to do something, I think it's quite difficult. And let me see if I can pull it off. Okay, what are we going to do today? We're going to discover and demonstrate, as almost always, the formulas for the sine of an addition of two angles, sine of alpha plus beta, the sine of a subtraction or the difference of two angles, sine of alpha minus beta, and also cosine of alpha plus beta and cosine of alpha minus beta. These formulas are not usually taught in high school, let alone their demonstrations. If they are talked about in high school, they really never show you the demonstrations, okay? Because most teachers think that uh, high schoolers will not be able to understand the proofs. So I'm gonna try to make you understand these ones. Okay, so why are these formulas useful? Well, because of this. Suppose that I give you this problem. Find the cosine of 75 degrees. Okay, so a lot of people are gonna fall into this mistake. They're gonna try to do something like this. They realize that 75 degrees in this case is actually the addition of two smaller angles, in this case 30 degrees plus 45 degrees, right? And as we have known already, as we have discovered, we can actually calculate the cosine of 30 degrees and the cosine of 45 degrees independently. Do you remember that? By the usage of those special triangles. I hope you remember. So people are gonna say, okay, if cosine of 75 degrees is equal to the cosine of 30 plus 45, that means that the cosine of 75 degrees is going to be equal to the cosine of 30 degrees plus the cosine of 45 degrees. And since we can calculate this one and this one independently, then I'm done with the problem. Well, no, that would be incorrect. This reasoning would be completely incorrect because of why? Well, we have never proven that the cosine of two angles, like in here, the cosine of this angle plus this angle, we have never proven that the cosine of alpha plus beta is equal to the cosine of alpha plus the cosine of beta. We have never proven this, and it is in fact incorrect. In the previous work, well, no, in this workbook of 3.4, there is a remark in one of the exercises in which I tell you that you can never assume something to be true. If you think that this is equal to this because you have an intuition or because you believe so or something, that is completely wrong. You can never assume something to be true in mathematics unless you have actually demonstrated it. That's the difference between mathematics and all other fields of knowledge. We require demonstration for every single thing. That's why it's so cool. Okay, so no, it doesn't work in this way. But what I'm going to show you in a moment is that there is another type of formula, okay, that will help us calculate this, which is the same as this, right? If we know the cosine and the sine of 30, and if we know the cosine and the sine of 45 independently, which we know, we will be able to pull off a formula for the cosine of the sum of two angles, okay? But it's not like the one I showed you before. This is not equal to the cosine of 30 plus the cosine of 45. It's not equal to that. So that's the importance of these formulas. They are very, very useful. Okay. So before we enter into the proper demonstration, I need to tell you about 3 steps, okay, context steps. prior to the demonstration of these formulas. And these are pretty simple steps, okay? But I need to make sure that you understand each of these three steps. Number one, the catheti, remember this is the plural of cathetes. These two are catheti. Estos dos son catetos. The catheti of right triangles of hypotenuse 1. So look at this triangle, guys. It's a right triangle, okay? It has cathetes A, cathetes B, and angle alpha. Okay, I'm calling this angle alpha. And also the hypotenuse happens to be 1. Okay, when we have this type of triangle with hypotenuse 1, you will see that these two cathetes, well, catheti, can be written in the following way, can be written very neatly in the following way. Look at this angle. And let me write the definition of the sine of such angle. By definition, that's opposite cathetes, which happens to be A, over the hypotenuse, right, which is 1. You see? So basically, we have discovered that sine of alpha equals A, or if I look at it the other way around, A is equal to sine of alpha. So basically, I have discovered that these cathetes, A, can be written as the sine of this angle. You see? So I can erase this, and I can write sine of alpha. And if I do the same with this other, I can discover the following. Look, cosine of alpha is equal to adjacent cathetes, which is B, over the hypotenuse, which is also 1. And therefore, cosine of alpha equals B. And I have discovered that these cathetes can be expressed or written as the cosine of this angle. You see how neat it looks? When you have a right triangle of hypotenuse 1, the catheti can be expressed as functions of this angle. Or this other angle, okay? It would be pretty much the same idea. So that's the first step. I hope you have understood this. Okay, this is done. Second step, the reduction of expressions or equations. I forgot to write in here, using the Pythagorean identity. So what do we have here? We have an expression, sine squared of alpha plus cosine of beta plus cosine of squared of alpha. How can we reduce this whole expression? By using the Pythagorean identity. Let's remember what the Pythagorean identity was. It's this. For any angle, sine squared of theta plus cosine squared of theta equals 1. Or any other angle, it doesn't make any difference, right? Sine squared of alpha plus cosine squared of alpha equals 1. Okay, so how can I use this property that we have already talked about in here? Well, look at this. We have sine squared of alpha plus cosine squared of alpha. And if I notice here, that's equal to 1. So basically, I can write this and this reduced to 1. And I have still this other term in here. So it's going to be plus cosine of beta. So this is the reduction of this by using the Pythagorean identity. They are equivalent. This whole expression is the same as this expression, but this is a reduced version of this one. Good. Now let's do the same for this equation. We have an equation here that contains the cosines and the sines of some angles. Let's see if I can reduce it. Well, we have a cosine squared of beta here, and we have a minus sine squared of beta here. What's going to happen if I bring this one to the other side? So let's do it. Cosine squared of beta plus sine squared of beta. And let me bring this one to the other side of the equation. So it's going to be cosine of alpha. And one more time, as you can see, all of this, according to my Pythagorean identity, this is going to be equal to 1. So all of this reduces to 1. which will be equal to cosine of alpha. So this equation, in the end, 1 equals cosine of alpha, is the same as this equation, completely the same, but in a reduced way. Okay, so that's how, and I'm just giving two very simple examples so that you understand how we can use the Pythagorean identity to reduce expressions or equations that involve the trigonometric functions of angles. So that's step one. This is step two, completely done. I hope you have understood. Very simple steps. And the third step is this. I'm gonna show you a video in which I'm gonna show you some geometrical arrangement of a circle and a triangle. Okay, I'm gonna show you something like this. I'm gonna draw a circle and then I'm gonna insert a triangle. Well, let me do that in yellow. I'm gonna insert a triangle in this way. Okay, often this is called a triangle at the center of a circle because one of the vertex of the triangle, in this case this one, is going to be fixed at this center of, well, at the center of the circle. It's going to be fixed, and I want you to note and to observe how I'm going to move the triangle and that particular remark about the two angles that are being formed, etc. Pay attention to the video. It's going to be very important, and try to understand everything I'm saying. Okay, let's watch that video. Okay guys, so what we have in here is a circumference or a circle of radius 1. Okay, this segment from here to here measures 1 unit. And what we have also is a triangle at the center of the circumference. What that means is that this vertex is always fixed. Okay, this vertex of this triangle is fixed at the center, and so it can rotate in this way. Okay, you must observe that these two sides, this side and this other side, are basically also radii of the circle. Okay, because these two sides go from the center to the circumference, as you can see. So both this side and this other side measure also 1 unit, which is the radius of the circle. Okay, and well, also we have this other, the remaining side of the triangle, which joins these two other sides. Okay, what is it that I want you to observe in this configuration? Well, the triangle, like I said, can rotate in this way. Okay, keeping this vertex fixed. Okay, try to observe how it rotates. And the important thing I want you to observe is this. Let's consider this triangle in this configuration, and we can observe that two angles are being formed, which is this one and this other angle. Let's call this angle alpha, and let's call this angle beta. Okay, I repeat, alpha and beta. So what's going to happen if I rotate my triangle counterclockwise in this way, so that now beta is reducing, as you can see, and the angle alpha is increasing. You see, now the angle beta, which is the one that I had in here in this position, is reduced to 0, and alpha, which maybe was up until this position, now it got increased. How much is this new angle going to be in total? Well, it's going to be alpha, like it was before, plus the reduction of beta. So this whole angle will be alpha plus beta. Let me do that for you again. This is alpha. This is beta. If I rotate the triangle now so that beta reduces, alpha will increase by the same amount. You see? So now this whole angle will be alpha plus beta. Okay, now that we have watched that video, and I hope you have understood how the triangle can rotate. Okay, it's the same thing. These two circumferences is the same thing that I showed you in the video. So what do we have here? We have an before and after steps of what I did in the video. The following circumferences have radius 1. Okay, I didn't draw the lower side of the circumference because it's not necessary. But let's analyze each of these two diagrams. First, this one. What do we have in here? Well, we have a circumference, like I said, of radius 1. Okay, so this is radius 1. And we have a triangle inserted, a triangle at the center of the circumference. And like I showed you in the video, we can form this angle alpha and this angle beta. This side is 1. Why? Because it goes from the center to the circumference, so therefore it's a radius. And I'm saying that by hypothesis, I'm constructing this diagram so that the circle has radius 1. So this is 1, and also this is 1. Perfect. Now, let's perform a counterclockwise rotation of this triangle, just like I showed you in the video. Okay, counterclockwise rotation, such that the angle B will be reduced to 0 and this side will lay on top of the negative x-axis, like so. Okay, so now my final configuration will be looking like this. And like I told you in the video, this new angle that's going to be produced will in fact be the sum of alpha plus beta. Okay, why? Because beta will be reduced to 0, will be decreasing to 0, and alpha will be increased by the same amount that beta reduces. If beta reduces completely, this angle alpha will increase beta. So therefore, this new angle will be alpha plus beta. Okay, perfect. We're getting closer to the developing of the demonstration. Okay, now, here comes the good part. Okay, look at this, guys. Look that we can form two triangles in here. Okay, this right triangle, and if I drop, well, this is a perpendicular to the x-axis, and if I drop from this point another perpendicular, I can form this other right triangle. Okay, good. Now, as I showed you a moment ago in one of those steps that I told you, if right triangles have hypotenuse 1, which in this case they do, okay, look at this triangle, it has hypotenuse 1, therefore we can express its catheti in terms, this catheti and this cathetus, in terms of the trigonometric functions of this angle. This cathetus can be expressed as sine of alpha, and this cathetus can be expressed as the cosine of alpha, and the same for this other triangle. This cathetus in particular, this one, can be expressed as the cosine of beta, and this other one as the sine of beta. Okay, now in red, what I'm gonna do is write the coordinates of that point and this other point, the coordinates. Can we get them? Yes. Why? Because we know the catheti of this triangle. All of this measures cosine of theta, and all of this height measures sine of theta. Therefore, the coordinates of this point are cosine of alpha. I said theta, right? That was a mistake. I meant alpha. Cosine of alpha and sine of alpha. Okay, these two are the coordinates of this point. I know it looks weird, but that's what it is, okay? If all of this measures cosine of alpha, then the x-coordinate of this point is cosine of alpha. And if all of this measures sine of alpha, then the y-coordinate of this point is sine of alpha, okay? Okay, and what about this other? Well, we know that that this cathetus measures cosine of beta, okay? But if you write in here cosine of beta as the x-coordinate, that would be incorrect. It needs to be minus cosine of beta. Why? Because we know that if we go from the origin towards the left, okay, in this direction, even though this cathedral measures cosine of beta, as a coordinate of this point, we have to put it negative. I hope you understand that. We have seen this already, this type of thing. And in this case, the y coordinate will be the same as this, sine of beta. Because it goes upwards, we don't need to write any minus in there. So we have this. Okay, so we have these two coordinates, guys. I'm sorry, we have the points. Well, I'm sorry, we have the coordinates of these 2 points. Okay, this is this point, the coordinates, and the coordinates of this point are these two. Okay, I know it looks complex. I told you this is complex, but let's keep it this frozen in here a little bit, and now let's go here. Okay, now this point, look at this point. Getting the coordinates of this point is very easy. And why? Because we know that the radius of the circle is 1. So all of these measures 1. But again, one more time, since we're going from the origin towards the left, the x-coordinate of this point should be -1. And the y-coordinate should be 0. So this one is very simple. And in here, I can again draw a triangle just like I did in here. This is a right triangle, okay? And I can get the coordinates of also this point. Why? Because I can get this cathedus and this cathedus expressed in this way. This cathedus can be expressed as the cosine of this angle, and this cathedus can be expressed as the sine of this angle alpha plus beta. Okay, now for convenience, I'm gonna write the sum of these two angles for convenience. Since I don't want to write too much, I'm gonna write it as gamma. Okay, this letter, new letter for you, it's gamma, alpha, beta, gamma, the first 3 letters of the Greek alphabet. And so I'm gonna say this, and with this little change, now I can write this instead. Cosine of gamma and sine of gamma. Okay, and now also in red, I'm gonna write the coordinates of this point. What are the coordinates of this point? It's gonna be cosine of gamma, comma, sine of gamma. Okay, so we have all of this stuff. Now, what is the next thing to do? Okay, this demonstration, guys, relies on this fact. If you notice, when this triangle gets rotated in this way, like first this is the configuration of this triangle, and then when we rotate counterclockwise, now the configuration is this. But you must agree that the measure of the sides never changes, okay? This side and this side and this side are conserved. They got only rotated, you see? So whatever this side measures is the same as the measurement of this side, because they are in fact the same side. You see what I mean? Now, how can I get the measurement or the length of this side? Well, we have its 2 points, okay, the coordinates of its 2 extreme points, this one and this one. And if we get the distance from this point to this point, the distance, then that's going to be the length of this side. And the same with this one, right? I have this point, I have its coordinates, I have this point and its coordinates. And if we get the distance from this point to this point, then I'm gonna be measuring the length of this side. Okay, and we know that this, or basically the distance from this point to this point, which is all of this, has to be the same as the distance from this point to this point, which is all of this. All of this is equal to all of this. And that's probably the most important part in this whole demonstration. So let's write down the distance from this point to this point. Let me call that distance 1. If you remember, I'm gonna remind you very quickly here, the distance between 2 points is equal to the following. You must remember, you have been working in the workbooks. Remember that this is the formula for the distance between 2 points with coordinates x1, y1, and x2, y2. Okay, so the distance 1, which is this one, it's gonna be the square root. I'm gonna keep it just like this for the moment, of x2. What's gonna be x2? It doesn't matter. I'm gonna choose this as 0.1 and this as 0.2. So this is gonna be x2. So let's start. Okay, minus x1, which is gonna be cosine of alpha. I close parentheses to the square plus open parentheses y2. What is y2? It's the coordinate of this point, right? Sine of beta. And then we have another minus, and then we have y1, which is now this, sine of alpha to the square. And all of this, the square root of all of that. Okay, that is the distance 1. Now the distance 2, which is this segment, I'm gonna call that distance 2. It's the same idea, the square root of all of this thing. Let me do the same thing. I'm gonna call this 0.2 and this 0.1. So we start with x2, which is minus 1, okay, and then minus x1, which is cosine of gamma to the square, plus y2 minus y1, this is y2, minus y1, which is this, to the square. Okay, so we have the distance from this point to this point, which is all of this, and the distance from this point to this point, which is all of this. And we already agreed that this segment or this side of the triangle is actually the same as this side. These two sides are completely the same. So basically the distance 1 should be equal to distance 2, and the square root of all of this should be equal to the square root of all of this. You see? So let me write that. Well, let me take one shortcut. If the square root of all of this is equal to the square root of all of this, then basically we can agree that what is inside the square root needs to be equal to what is inside of this square root. It's kind of like this. If you know that the square root of a equals the square root of b, then a is equal to b. And I can write that right away. So I'm gonna write all of this, what is inside the square root. It's equal to all of this. I'm gonna dispense of this 0 and just write minus sine of gamma squared. Okay, so we are in here. Okay, basically what I wrote is that all of this is equal to all of this according to this property. Okay, and that's my work. That's up until this point, that's gonna be my work. What are we having here, guys? We have an equation and we have some binomials. Okay, this is a binomial to the square. Binomial, I forgot in here something. going to be sine of alpha to the square. Okay, another binomial to the square equals another binomial to the square plus this thing to the square. What do I want you to do now? Okay, it's gonna be your work. I'm not gonna do the rest of the proof. I need you to do it, to try it. Okay, what you're gonna do is expand these binomials to the square. So basically raise each of these binomials to the square. You're gonna get a very long thing, and then you're gonna use the Pythagorean identity in order to reduce as much as possible this whole equation, okay? And what you should be getting in the end, is the following. I'm gonna tell you right away what should be the final result. The final result that you should be obtaining is this. You're gonna be obtaining that the cosine of gamma is equal to the following. The cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. And if we know that gamma is equal to alpha plus beta, then we can write this. Cosine of alpha plus beta equals, well, to the same thing, the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. This is what you should be getting in the very end of this process. It shouldn't take you too long, maybe 5 minutes, 5, 6, or 7 minutes. Give it a try. I'm gonna wait for you, pause the video. Well, no, I'm just gonna stop the video right now, and you should be getting to this conclusion. So let's do it.